Swayam Prabha. Digital India. Educated India.
Right. So, what we try to do over the last lecture of today and the first lecture of tomorrow is kind of pushing a one semester course into 2 lectures, right. Okay. So, like we would kind of I'd start by saying to you that if you want to do modern day computer science, it's like the days when we were students, only discrete mathematics helped. With discrete mathematics you could just do computer science. Now computer science has matured, it has picked on new application areas. Now if you don't do data science, you tend to fall behind, right. But I come from a generation where where people still looked at classical problems and stuff like that. But nowadays as you people grow into and the subject grows, newer and newer fields come, newer and newer challenges come. So computer science these days has picked on other 2 branches of mathematics, of which I will not talk of linear algebra in this 2 weeks. So, we will talk of probability and show to you how probability helps in computing. So, the focus of the lecture of these 2 lectures is to give you an overview of the probability that you would need during this course. So, tomorrow first lecture would be again on probability, on a particular thing of probability that would be much in use, at least for this week and some part of the next week. And then we would show to you how algorithms uses probability. Fine. So, let us start with an example, say. So, I give you a coin, right, and I say it is an unbiased good coin. So, that means the probability of head is half and the probability of tail is half, and you keep on tossing this coin, say, till you get a head. On the now see the point that in the worst case it might so happen that all of your tosses might result in a tail, okay. But in the limiting case you might say that it is highly probable that I will have a head. But let us forget about that, but think of an kind of an average case, that what is the expected number of tosses that you might need to do before you get a head? 2, right. Okay. Now, I change the problem a little bit. I say I give you a coin such that the probability of head is now not half, but it is 1/3. And I ask the same question again, on the expectation how many throws do you require? Now, I generalize, I tell to you that well the probability of getting a head is P, on the expectation how many tosses do you want to make? Half was 2, 1/3 was 3, so P should be 1 by P, right. It should be a number greater than 1, right, you cannot make. Now, what is the proof of this one? It was very well saying that well my intuition tells me that with a coin of probability head being half, I require 2 throws, for 1/3 it is 3 throws, for a probability of P it is 1 by P throws on the expectation, remember it, on the expectation. Now, I have to prove this, right. Without proof this is just an assertion. So, this kind of things we will see in this next 2 lectures. Okay. Now, before I go into formally setting up things, may I know how many of you know what is a random variable? Okay, so what is a random variable? Yeah, so you come from a mathematics background, is it? This is the first time I have heard such a correct definition. It's like, so most people say that a random variable is a variable that takes values randomly. Well, that is not the case. It is a function from somewhere, obviously if it is a function, it will take a value from somewhere to somewhere, we will see. Now, we will at a point of time, maybe over the course of lectures or over tutorials that Uddala could conduct, we will prove this result, that the expectation is 1 by p. But at least in this course, I mean during these 2 lectures of mine, if I am not able to prove this, but I will at least set up things such that you can prove it in the tutorial. Okay. So, we would take an axiomatic approach to probability. Now, what is an axiom? Statement assumed without a proof. All of you must have seen an axiom at some point of your life. What is it? What is it? You must have seen it. Geometry. Geometry. You never questioned when your teacher said there is only one line between 2 points. That was an axiom on which your Euclidean geometry was built. So, similarly, this subject of logic basically sets up this thing where you take some axioms and build theories on this. So, if you question those axioms, if you say those axioms are not true, your theory does not follow, right. So, we will set up an axiomatic approach and then develop things and then kind of prove results that which you already knew, fine. So, the setup is you have an experiment which has certain outcomes, and the moment we say this, we start talking in terms of sets, right. So, probability would be over a set. Think your favorite experiments, throwing dice. If you are in computer science, say you have a graph and say you are picking edges randomly, that is an experiment, right. You are say sorting, tomorrow you will learn quick sort. So, all of you know quick sort, right. Anyone not knowing quick sort? No, okay. So, if you are doing randomized quick sort, you pick an element to be the pivot at random, uniformly at random. So, this is an experiment, right, about picking an element uniformly at random. So, you have experiments and the outcome, all possible outcomes of that experiment forms the sample space. And then you have a probability law which kind of assigns values to these events. Say for example, in your dice case, you say that all of your throws are equally likely. So, your sample space has 6 points, each one with a probability of 1/6, and then you can build complicated events over this sample space. Okay. So, what is an event? It is a collection of possible outcomes, or even put more succinctly, it is a subset of the sample space, fine. Okay. Now, as me and Venkatesh would want everyone to be on the same page, it is like I will go a little slow at the beginning, and at any point of time if you do not understand anything, do ask questions, right. Do not hesitate in asking questions. however foolish they might be. Right? Never stop yourself from asking any question that you feel is legitimate. Ask it. Fine. Now, what is our axiomatic approach? Right. So, probability space I would say is a triple consisting of the sample space. This F is going to be kind of subsets of the sample space and a probability. Now, we will make this P follow certain rules. So, omega I have defined to be the sample space. This is collection of subsets from sigma and P is the probability. So, I would say that P is a probability measure which takes F to 0 1, right. So, you have three things: one, a sample space, then a collection of subsets over the sample space, and a probability function taking the from any subset F of F to 0 1. You have some requirements on F. So, the requirements are the null set belongs to F and the sample space also belongs to F. So, call them to be requirements on F. Okay. Second is, if you have a subset in F, its complement should also belong to F. And third is, if you have subsets, well, it's like it would suffice if it's countable, but for our cases we would focus only on the discrete case where it's countably finite, right. Until and unless we explicitly mention, everything is countably finite here, because it is a discrete world, it is a computer world, so you can count things. Okay, the requirement is for such sets their union also belongs to F. Union over this belongs to F. So, these are the requirements on F. Now, about the axioms. These are some requirements on P. First, so P is a, as I said earlier, is a real valued function satisfying the following. First is that it, for any event A, its probability lies between 0 and 1 for any in F. Second, that over the sample space the probability is 1. Third, and this is the most important, because all the results that you know actually comes from this. So, again I make it for any countable set of events. While writing, I would not be always too correct. So, this countable set of events A1, A2 should be belonging to F, right. So, I am talking of subsets in F. So, they are disjoint. That means there is no intersection, right. The axiom says you can now add probabilities. Fine. So, disjoint means if you take any AI and any AJ, their intersection is a null set. Yes, union of, I did not get you. See, AIs are sets. So, union of sets are defined, well defined. Now, what did I say? Probability is a measure, is a function from the sample space to 0, 1. So, the left side is well defined. Now, if you look into the other side, probability of AI is again very well defined. What I am doing is I am just taking sums. Yes, equal to, and this is an axiom which you will not question. Now, there is a counter punch to this which I will come to later on, which is known as, some people call it in terms of Boole's inequality, some people call it, we call it to be union bound, and myself or Uddala could do, I think we have few exercises on union bound. The union bound actually says that if these AIs are not necessarily disjoint, then the equality is replaced with a less than equal to sign. Now, whatever this, so I will come to that later on. So, but as people raise questions, so this is an axiom. What I am saying is you have events in your sample space that are disjoint, then you can just add their probabilities. Fine. Any questions till now? Okay. So, let us go forward. Now, using this you can do quite a lot of things. First, how do you prove? Yeah. The summation can grow more than, no, but I have kept the second thing, right. Probability of the sample space is equals to 1, and so your union of disjoint events where each event is a subset of sigma, this union cannot grow beyond the sample space, right. So, this sum cannot get over the 1, and I have not talked in terms of the indices, because whatever these indices are, the same indices come here. If here it is I equals to 1 to n, then there also it is I equals to 1 to n. Okay, what about this exercise? How do you prove this? You can even do it simply, right. You have one axiom which tells you that probability of sigma is 1, right, and the complement is also in the, so it follows, right. So, try this exercises. So, similarly you can think of this so you can easily prove this from axioms, right, because A and A complement are disjoint sets, so they would sum to 1, hence the result follows. This is a result I think which you might not have seen earlier. Okay. And if it is strict, then this holds, if it is, then this holds, right. Why? See, the point is, when I am taking an axiomatic approach, you can't use any argument apart from the axioms, and probably some arguments on sets that you know. So, if think of this, A is a strict subset of B, right. So, that means now you can write B as A plus B minus A. These two are disjoint sets. So, probability of B equals to the sum of two probabilities, out of which one is probability of A and the other is of some probability. Your first axiom tells you that any probability has to be positive, greater than 0. So, there is probability of B equals to probability of A plus a positive quantity or greater than equal to 0 quantity. So, then probability of B has to be more than probability of A, fine. Okay. So, do this as exercises. Okay. So, I would not write this. So, whenever I just forget about, so when I write this, it actually means intersection, right. For to have a clarity on the notation, if I write two sets side by side, it means intersection. Yeah. So, come on, prove this using axioms only. So, again think of writing A as, yeah. So, use A complement B. So, A union B is full of A, right, and then B, get rid of the part that B is overlapping with A, that is B intersection A complement. These two are disjoint, fine. And now you can write A complement B in terms of B as well. So, that is how A intersection B gets into the expression. Quickly do it. So, if you need help on this, then we will again do it in the tutorials. Okay. So, all of you probably know this, right. It is only that possibly setting things up in an axiomatic framework and deducing results, this thing you possibly might not have encountered, fine. Now, what about extending this? So, so this is known as principle of inclusion and exclusion, and now you want to write union of AI in terms of many intersections, and so this is summation of PAIs, right. Now, if you add this, if you write this, obviously you understand which side is greater? The right side is greater, right, because we talked of this Bull's inequality or union bound. So, you will have a subtracting term, that is probability of say AI1, AI2, right. There would be how many terms in there? How many such terms? N choose 2 terms, right, because you would look at all pairs of sets A1, A2, A2, A3, A3, A1, so on and so forth. Now, when you look into this, the right side is now smaller. Then you add another term, and this goes on. Or else you can write it as just A1, A2 up to AN, right. Now, if you are going to compute this brute force, how many terms are in there in this expression? Asymptotically tell me, how many terms are there in this expression? Huh? Right. So, you are looking at, so look at the first sum. How many terms are there? N choose 1 terms. In the second sum, NC2. In the third sum, you go up, right? And this is like, this sums to what? 2 to the n, right? Because you are looking at all possible subsets of n. So, computing this brute force is not a very easy proposition. Whenever you encounter such expressions, be a little cautious. If you are handling the general case, be a little cautious. Okay. Exercise is prove this. How can you prove this? Again, start from axioms. Your base case would follow from axioms and then use induction on n, where n is the number of sets you are handling. Let us now quickly do, as Venkatesh said in the morning, it is like it's good to have examples and tutorials. Derangement. So, all of you know what is a derangement? So, arrangement is rather I would say derangement is completely opposite to what arrangement is. It's total mess, right? And what is the total mess? You have say n envelopes, as she said, and n letters, each letter designated for its particular envelope, right? So, letters to Calcutta, to Coimbatore, to Chennai, to Mumbai, so on and so forth, envelopes marked with the addresses for each letter. Now, I want to figure out, well, there is obviously you understand there is a inherent counting problem to it, that I want to count the number of cases in which no letter goes into its correct envelope. That is a total mess. So, this is derangement. Okay. Now, you can state derangement in terms of permutation. Think of permuting the numbers from 1 to n. So, you have n positions and you have this n numbers and you want to permute them such that they go into those slots. So, a fixed point, I will say a fixed point of a permutation is the case where the ith element goes to the ith spot, and the derangement is one where the ith element does not go to its ith slot for all I running from 1 to n. So, there is no fixed point of the permutation. When that happens, it is a derangement. Fine. So, this problem is clear. Okay. Now, the question is, I randomly now put the letters into the envelopes. I pick a letter from this envelope. So, I pick the first letter, I randomly pick one, put the letter in there. That envelope is crossed, I take the second letter, because it is a permutation. So, two letters cannot go to the same envelope. So, I take the second letter, again pick an envelope of an envelope at random from the remaining envelopes, put it there. This continues. Now, I ask you, what is the probability that this random assignment was a derangement, or probability that any random assignment gives you a derangement? Yeah, we have to figure that out. So, this is what I want, probability that a randomly chosen permutation is a derangement. This is what I want. Now, what do you think? This probability should be how much? Give me a guess. Give me a guess. It should depend on n, right? What? Give me a guess. Give me a hunch. The answer would be something like this. No, that is the deduction. Give me a hunch of what should be the answer like. I look at this and then I will subtract 1, rather I will subtract this from 1, right. Now, look at this event. AI is the event that the ith letter goes into the ith position, and then 1 by n is the correct answer. So, you feel 1 minus 1 by n is the correct answer. Okay, this is a hunch. We will see 1 minus 1 by n. At least I have one answer. Other answers?